Let us look at expansion for sine alpha and cos alpha. What I mean by expansion is series expansion. Taking the imaginary part of the binomial expansion for cos theta plus I sine theta to the power of n. This we saw in the previous session. So we have sine n theta is equal to nc1 times cos to the power of n minus 1 theta times sine theta minus nc3 times cos to the power of n minus 3 theta times sine cube theta and so on. So we have odd powers. Now let's expand the coefficients. So we have sine n theta is equal to n times cos to the power of n minus 1 theta times sine theta minus n times n minus 1 times n minus 2 divided by 3 factorial times cos to the power of n minus 3 theta times sine cube theta and so on. The general term would be t sub k is equal to, the signs are alternating, so minus 1 to the power of k times n minus 1 times n minus 2 times dot times n minus 2k divided by 2k plus 1 factorial times cos to the power of n minus 2k plus 1 theta times sine to the power of 2k plus 1 theta. Now here we have one factor, another factor, another factor, and another factor. So let's look at them one by one. Let's focus on the binomial coefficient. Taking out n from each of the factors, we get n times 1 minus 1 by n times n times 1 minus 2 by n and so on up to n times 1 minus 2k by n. How many n's are there? There are 2k plus 1 n's are there. So we have n to the power of 2k plus 1 times the rest of the factors. So that was the binomial coefficient. Let's look at the sine factor. Let n theta be equal to alpha, which implies theta is equal to alpha by n. So sine to the power of 2k plus 1 theta is equal to, substituting theta equal to alpha by n, sine to the power of 2k plus 1 of alpha by n, which is equal to this expression. Now, how did we get this? What we have done is we have multiplied and divided by alpha by n to the power of 2k plus 1. So we have in the numerator this and in the denominator alpha by n to the power of 2k plus 1. The idea is to get this sine of alpha by n divided by alpha by n. We have to get rid of this denominator n to the power of 2k plus 1. So we multiply both sides by n to the power of 2k plus 1. Then n to the power of 2k plus 1 and n to the power of 2k plus 1 gets cancelled. And we have n to the power of 2k plus 1 times sine to the power of 2k plus 1 theta is equal to alpha to the power of 2k plus 1 times sine alpha by n divided by alpha by n, the whole to the power of 2k plus 1. Now we have the cosine factor, this one. Cos to the power of n minus 2k plus 1 theta can be written as cos to the power of n of alpha by n times cos to the power of minus 2k plus 1 of alpha by n. So we have addressed all the factors. The first factor, that is minus 1 to the power of k, remains as it is. So we have t sub k equal to this expression. Now let n go to infinity, which implies any finite number divided by n goes to 0. So what's going to happen when we take n to infinity with respect to these factors? 1 minus j by n goes to 1 for any fixed j. Sine alpha by n divided by alpha by n goes to 1. That means 1 to the power of 2k plus 1 is also 1. Now cos alpha by n, since alpha by n goes to 0, cos 0 is 1 and 1 to the power of n is 1. And similarly, cos to the power of minus 2k plus 1 of alpha by n goes to 1. So what we are left is t sub k going to minus 1 to the power of k times alpha to the power of 2k plus 1 divided by 2k plus 1 factorial. So what will sine alpha be? Sine alpha will be equal to t sub 0 plus t sub 1 plus t sub 2 plus t sub 3 plus t sub 4 and so on and on and on. Now let's use this to figure out what these terms are. Sine alpha is equal to t sub 0. So minus 1 to the power of 0 times alpha to the power of 2 times 0 plus 1 divided by 2 times 0 plus 1 factorial, plus minus 1 to the power of 1 times alpha to the power of 2 times 1 plus 1 by 2 times 1 plus 1 factorial, and so on. Now simplifying that, we get sine alpha is equal to the series minus 1 to the power of k times alpha to the power of 2k plus 1 by 2k plus 1 factorial, which is equal to, by simplifying this, we get alpha minus alpha cube by 3 factorial plus alpha to the power of 5 by 5 factorial, and so on. So we have found the expansion, series expansion of sine alpha. So here alpha can be looked at as alpha to the power of 1 by 1 factorial. Now, similarly, by equating the real part, we equated the imaginary part. Now we equate the real part, we can arrive at cos alpha expansion. What we'll end up with is cos alpha is equal to the series minus 1 to the power of k times alpha to the power of 2k by 2k factorial, which would give us 1 minus alpha square by 2 factorial plus alpha to the power of 4 by 4 factorial, and so on. That was series expansion for sine and cos. Now, if you found this session helpful, please do like, share, and subscribe. Questions, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.